You've clicked onto the Ohm's Law post-lab video. So this video should be primarily viewed after having completed the Ohm's Law lab in class. In this lab, we try to answer two questions. First of all, what is the relationship between electric pressure differences, also called potential difference, and the charge flow rate, which is called the current? And we also want to ask, does a large electric pressure difference mean that there will be a large flow rate or a large current? Quick review of the lab. In this lab, we had a resistor that you were given, and the value of that resistor was recorded in the lab. And then we had a current probe to measure flow rate right in the same path as the resistor. So we would say the current probe was placed in series with the resistor. And then we made a connection on either side of the resistor with the voltage probe so that we could measure the pressure difference between this side of the resistor and this side of the resistor. See how much higher this side is than this. So we could record that. And then we had a power supply which generated a pressure difference, this side being higher than that side. Now the way the lab was done is you set various pressure differences across the resistor and then measured the flow rate that you got. And we had many different voltages, and we measured the flow rate that you would get in response to those voltages. And then you made a graph of voltage versus flow rate. So here's one such graph that you would get. Notice I did various potentials or pressure differences or voltages and measured the flow rate or the current that resulted. I used a 30 ohm resistor for this graph, and if I notice this, I can see that as the pressure difference goes up, the flow rate goes up. And so I can see actually that I'm going to get a straight line. And so my first answer for this resistor is that electric potential or pressure difference is directly proportional to flow rate. In other words, if I double the pressure difference, I double the flow rate. Now the instructions for the lab said to choose linear fit and get the slope of it. And notice that that's what I get. And we were supposed to record the slope and the y-intercept. So if I do that, I can see that the slope is about 30.9. It says volts per amps. And the y-intercept is really very, very small. Now that makes sense to me. The y-intercept really should be 0, because what the y-intercept would actually mean is that if I don't put any pressure across the resistor, in other words, if that's 0, I shouldn't get any flow rate. So I would expect the y-intercept to basically be 0. So I recorded that, and I noticed that the slope, this is a really important thing, of this line is very close to the resistance of my resistor. So at this point I can conclude that electric potential difference or pressure difference or voltage is directly proportional to flow rate, and that the slope of a graph of electric potential on the y-axis and flow rate on the x-axis gives me the resistance of the resistor that I'm using. So let's try this out for a different resistor. This resistor is 55 ohms, and I notice first of all that this line is a lot steeper, noticing, although the scale is different down here, but that more pressure is needed to produce the same flow rate. I notice that it's still directly proportional, so I can see that as the pressure goes up, so does the flow rate. And I can see once again that the slope of this line gives me the resistance of the resistor. So it appears that electric pressure difference and flow rate are directly proportional, and that if I make a graph of them, the slope of that graph is going to give me the resistance. Well, like the name of the lab says, one of the goals of the lab is to see if Ohm's law is applicable to resistors. So Ohm's law says that the current through a resistor is proportional to the voltage across the resistor. So the way we would see that is if we made a graph of voltage across the resistor on the y-axis and current through the resistor on the x-axis, and proportional would mean that we get a straight line, which we have gotten. Now, if that happens and we do get a straight line, then we can use this formula to build the formula for Ohm's law, because that's the formula for a straight line, which we have. Now, B stands for the y-intercept, and as we said, the y-intercept on our graph means if you don't have any voltage, you shouldn't have any current. So we agree with that. So the y-intercept should really be 0. So I have y equals mx. Now, what we graphed on the y-axis is we graphed electric potential, or pressure difference. So I'm going to use the word potential, although it's certainly a good idea mentally to keep referring to this as the pressure difference. So it's a potential difference is the science name for it, but it's the pressure difference across the resistor. And that's equal to the slope of the line, which as we saw is the resistance. And then that resistance is multiplied by whatever you graph on the x-axis, which is current or flow rate. So we've built this formula. The potential, measured in volts, is equal to the resistance, measured in ohms, times the current, which is measured in amps. So now let's write Ohm's law as a formula. And what we have so far is that electric potential, or pressure difference, is equal to the flow rate times the resistance. So this is one way to write Ohm's law. On your reference tables, what they do, however, is they solve this for R. So what I would do is I would divide this both sides by I, and what I would end up with is that R equals V over I. And so the way we would say this is the resistance of a resistor is the ratio of how much pressure you put across the resistor to how much flow rate you get. So high resistance means you have to put a big pressure difference across the resistor to get a little bit of flow rate. A low resistance means if you put only a small pressure difference across the resistor, you get a lot of flow rate in response. So this is another way also to define 1 ohm of resistance. So what we could say is if you have a 1 volt pressure difference across your resistor, and in response to that pressure difference, you get 1 amp of current going through the resistor, then we would say your resistance is 1 ohm, which is the way we abbreviate ohm. Okay, let's just see the relationships between the different variables in Ohm's law. So the variables are the pressure, or potential, represented as a V, the flow rate, which is represented with an I, and the resistance, which is represented with an R. As we change the pressure, which is going to be changed here, we're going to see the size of the V going along with this, and we're going to see what kind of flow rate we get, how the flow rate changes. Flow rate is going to be measured down here. So let's see what that relationship looks like. As the pressure is increased, the I gets bigger, there's more flow rate, there's more pressure. As the pressure goes down, flow rate goes down. So we can see those are directly related to each other. As voltage goes up, current goes up. Now resistance, as the resistance goes up, the current goes down. We can see that current and resistance are inversely related. More resistance, less flow rate. So to see how this would work in a problem, let's say we were asked how many volts of pressure difference does it take to get a current of 2.53 amps to go through a 67 ohm resistor. So my first thing I'm going to do is I'm going to write Ohm's law as it appears on my reference tables. And then I'm going to substitute into the formula with units. So R is the resistance. I have 67 ohms. And that equals V, which is what they're asking me for, divided by 2.53 amps. So if I rearrange things to get the V by itself, I multiply both sides by 2.53, and I get V equals 2.53 amps times 67 ohms, and that's going to equal, rounding off, 170 volts. Well, the last question asked in your lab is, do all resistors obey Ohm's law? And to do that, we replaced the resistor with a light bulb, and we made a graph of pressure difference versus flow rate for a light bulb, and it looked like this. Now, the first thing you notice about this is that at the beginning, it curves, and then it kind of goes straight, so that the slope here is really pretty small, but then the slope gets greater and greater and greater. Now, Ohm's law says that electric potential or pressure difference is directly proportional to flow rate. And that would mean, if that were true, you would get a straight line. Now, this line curves. We also know that Ohm's law tells us that the slope of that line would give us the resistance. So this is a small slope, and this is a larger slope. So that indicates that the resistance actually changes for this light bulb. So this light bulb does not obey Ohm's law. Now, they actually had us in the lab, first of all, find the slope for just the first 3 points. So you select the first 3 points, and then you do a linear fit. And notice that if I check the slope of that out, the slope of this looks like it's just over 7 volts per amp, which is an ohm. So that's a relatively low resistance, which I can see because I have a relatively low slope. But then I was asked to select the last 10 points and do a linear fit on those and see what the slope is at the very end. Now when I do that, I notice that this slope is like just over 49 ohms. So at the end of this, the resistance is about 49. At the very beginning, when you started, very low voltages, very low flow rates, the resistance was just over 7. So a light bulb does not obey Ohm's law. Now, we can learn a really important thing here from realizing that at the beginning when you turn the light bulb on, the resistance is low, and at the end the resistance is high. Because we could ask, what's the difference between the light bulb when you have a high flow rate and the light bulb when you have a low flow rate? And one thing you could observe while you're doing this experiment is the light bulb is lit here and it's not on here. In other words, the filament here is not hot enough to glow. But once the filament is glowing, once the filament is hot enough, then the resistance is high. So we learn a really, really important thing here. We saw that as a light bulb gets hotter, in other words, it's brighter, its resistance actually increases. So light bulbs don't obey Ohm's law because pressure and flow rate are not directly proportional. In other words, the resistance or slope goes up with the light bulb. If it was directly proportional, the slope would stay one number. So light bulbs don't obey Ohm's law. Now, why this is makes sense if I think about what hotter might mean in a material. If a material is hotter, the atoms that make up the material vibrate more. They're moving around more. And that makes it more difficult for charges to get through because they keep crashing into the atoms. It's hard to get through it. So if it's harder to get through the material, then that means the material has more resistance. So this actually makes sense.